Okay, so today what I'd like to do is to actually, I've been sort of messing around with some of these integrals, and I wanted to show you just how you can do one of the examples that we wrote down yesterday, and it's kind of a lengthy example to do. So I just want to show you how you could do this if you didn't look up how to do the integral in a table of integrals or something like that. So remember that when we were trying to do the arc lengths for y equals e to the x, one of the integrals that you get, it's a definite integral, but one of the integrals that you're going to end up having to deal with is going to be, well, you have dy by dx, this is going to be equal to e to the x anyway, so you end up with an integral from a up to b of the square root of 1 plus e to the 2x dx. And how do you end up actually solving that integral? Because it's really not entirely obvious what you would do. Well, let's go ahead and take a look at how we can actually solve this integral. Now, one thing you might do is you might just look the thing up or something like that. And, you know, I'm not opposed to looking up integrals in a table of integrals or something like that, because that, as long as you know how to do them, that's okay with me. But I figure we should go through and we should do one of these integrals in detail at least once while we're talking about this stuff. So let's work through this one. Now, the first thing that I'm going to do is I'm going to make a U-Substitution. So actually, I'm going to ignore the fact that this is a definite integral for now. We're just going to figure out the antiderivative. And then when you have to deal with bounds, you can deal with bounds in the usual ways. So what I'm going to do now is I'm going to say, let's let u be equal to e to the 2x. And if I do that, then what we need to do is we need to figure out, well, what is dx? Now, the thing is that this means that x is 1/2 natural log u, so dx is going to be equal to du over 2u. So this is then going to become, and I want to make sure here that I don't get anything confused, because if we mess this up, it's going to get really nasty. Square root of 1 plus u divided by 2u du. And there we go. Okay, so we've gotten things simplified a little bit here. Now we're going to do another substitution here. What I'm going to do here is I'm going to make the substitution v is equal to the square root of 1 plus u. And what I want to claim here is that this integral, so we can calculate dv, which is going to be du divided by the square root of 1 plus u. If you do a bit of work here on this, what we find, checking my notes, is that this integral in terms of v's is going to come out to be 1/2 integral, and let me make sure that I've got this right again, I forgot a factor of 1/2 here, didn't I? 2v squared divided by v squared minus 1 dv. And then what I can do is I can rewrite this after a bit of work here. We can say this is going to come out to be, let's see, we want to factor out some stuff here. What did I factor out again? Sorry. Again, these are really complicated. That's why we're going to be kind of carefully following things along. We can cancel the 1/2 and the 2, so that works nicely. So this is going to become the negative integral of v squared over 1 minus v squared dv. So what I did here is a little trick where I pulled out a negative from the denominator. And then what we can do is we can say that this integral is going to become the same thing as negative of this whole big mess of stuff that we're going to have. This is going to be 1 over v squared minus 1 plus the integral of, minus the integral of 1 dv. Now, this integral we can deal with by partial fractions. And when you deal with this integral by partial fractions, what you're going to get is that this integral is going to come out to be natural log of v plus 1 over 2 minus natural log v minus 1 over 2 plus a constant, but we're going to ignore that for the moment. And so this is going to, I forgot my negative out front, so let's make sure we have the negative out front. And then we're going to be subtracting off v and then adding a constant to it. So now what we need to do is we need to go back and we need to rewrite everything back in terms of x's. And when you do that, what you find is that you are going to end up with negative 1/2 times the natural log of the absolute value of, I'm taking forever here looking at my notes, but when you write everything back in and you simplify it, what you end up with is the absolute value of square root 1 plus, plus e to the 2x plus 1. And then you have plus 1/2 natural log absolute value square root of 1 plus e to the 2x minus 1. And we do need to make sure that these are absolute value signs here. So when you deal with the definite integral bounds, remember, you're going to have to make sure that you're careful about absolute value stuff. And then, of course, we're just going to have plus square root 1 plus e to the 2x. And then we're going to have plus a constant. So there we go. That is sort of how you do this antiderivative. Now, I did skip a few of the steps in the middle, or I didn't really skip the steps, but I left a few of the steps where you have to work out some of the details to get there. But that's kind of how you do one of these integrals by hand. Now, what you might be wondering then is, if you have to do something like this, what do you really do in practice when you have to do this? Well, the answer would be you look at a table of integrals. So let me momentarily grab the book here, and we can kind of take a look at what are the various tables of integrals things that we can work from. And first I need to find the table of integrals. Where is the table of integrals? So after a moment of looking, I realized that my electronic copy of our textbook doesn't have the table of integrals in it. But the point I wanted to make about the table of integrals problem, see, the issue is I found some other tables of integrals while I had this pause so that I could look for them. And the original form of the integral doesn't show up in that table. And in fact, several of the forms that we got into don't show up in the table either. So the thing is, a table of integrals is not always going to be able to just fix things for you. Like, the problem is you may have to rewrite your integral quite a bit before you find something in the table of integrals that's going to allow you to actually do the integral, okay? And that's where I want to go with this. To use a table of integrals, you still need to know a bunch of integration techniques, because you need to be able to rewrite things in terms of other integrals. When I'm looking at these tables of integration that I found, I'm finding that for this problem, I still had to do the same kinds of rewriting as we did. I just got to skip a few of the steps like partial fractions and things like that. Some of the more basic steps, although tricky steps and long steps, so the table of integrals is really good. It helps us a lot. But you can't just rely upon, I can just look up the integral whenever I want to. No, it's going to take more work than that. So when you are doing these arc length problems in particular, you're going to find that even with a table of integrals at hand, the techniques from chapter 7 are going to be really, really important for you. And even a computer algebra system will sometimes not want to do the integral for you, and you may have to rewrite it several times before the computer algebra system will be able to handle doing that integral. So I wanted to show you this kind of example where, hey, this is not the sort of thing, I've erased the integral long ago because I don't have much space to write. But that integral that we started with, the integral of square root 1 plus e to the 2x dx, this is not something that you can just look up. You have to do a bunch of work to rewrite it, and that's why it's so important to know those techniques. All right, so this has been a really, really brief video on that topic, because what I'd like for you to do is really just to spend some time playing around with different arc length integral examples and things like that. So go on to Paul's Math Notes website and figure out what you have, like go to his practice problems, spend some time studying those practice problems. He doesn't actually have that many because these are really quite tricky problems. And practice writing down the integrals, and then think about, how would you do this integral? How could you rewrite it in a way that you could actually look up the result on a table or something like that?